Hello, and thank you for viewing this webinar. My name is Andrew Earls, and I am one of the authors of Chapter 4 of Volume 3. I am a senior stormwater engineer and a hydrologist with Wright Water Engineers. The purpose of the webinar today is to provide an overview of updates to the fact sheets in Chapter 4 of Volume 3. This is the second webinar in an on-demand series related to updates to Chapter 4. This webinar focuses on the fact sheets, which provide design criteria, procedures, and guidance for stormwater control measures, or SCMs, ranging from grass buffers and swales to permeable pavements to green and blue roofs. Future webinars will go into greater detail on some of these fact sheets. This webinar provides an overview. In addition, we're planning to hold periodic office hours in the future to allow users to post questions related to specific aspects of the chapter in an informal online setting. This is a flowchart that explains how Chapter 4 is used in conjunction with the fact sheets and other sections in the My Life Flood District's manual to design stormwater control measures. We covered this in the first webinar related to the front section of Chapter 4, but I've included it again here because it really is important to understand this relative to the fact sheets. The intent is not for fact sheets to be standalone cookbooks for SCM design. The fact sheets must be used in conjunction with other sections of Chapter 4 and other chapters in the Urban Storm Drainage Criteria Manual. This allows stormwater designers flexibility in combining different SCM components into high-functioning SCMs that will be assets to the surrounding community. We have updated many of the criteria related to infiltration SCMs to enable broader use. It all starts with selecting the type of SCM. The numbering on this chart indicates an order of preference for SCMs, always starting with runoff reduction and then considering unlined infiltration systems, lined infiltration systems, and then finally ponds. This order of preference is related to runoff reduction and pollutant treatment capabilities of different types of SCMs and a philosophy of treating stormwater runoff near the source where it is generated. Receiving Pervious Areas, or RPAs, is a new fact sheet created from the previous grass buffer and grass swale fact sheets. RPAs include buffers and swales, but are also more broadly defined in this new fact sheet. RPAs are defined as any pervious area that receives runoff from an impervious area, and these are really important for disconnection of impervious areas. There are many pervious areas in the built environment, and planning how to use these areas to slow down and infiltrate runoff is really important. RPAs act as runoff reduction SCMs. They slow down runoff through vegetative resistance, and this in turn allows for infiltration. For buffer type RPAs to work properly, sheet flow conditions must be provided. If flows concentrate, only a portion of the vegetated surface will effectively be being used for infiltration. So we have to spread out the flow using things like level spreaders or slotted curbs. Even for swales that convey concentrated flow, you can consider using the banks of the swales as buffers to allow runoff from upgradient areas to enter the swale as sheet flow. Vegetation is important for proper functioning of RPAs. We really want to have dense turf grass. Typically, we avoid bunch grasses because those tend to leave bare ground between the plants, and this can create preferential flow paths. Irrigation is going to be needed even if you're using natives, at least for initial establishment and potentially in the future during extended drought periods. Another thing to note on this slide is the importance of providing a vertical drop. We call this out specifically in the criteria, and the photos on this slide illustrate why that's important. As you can see here, we have a slotted curb, and the photo on the bottom shows that the grass has grown up and is obscuring a lot of the slots in the curb, impeding the flow of runoff onto the buffer. Therefore, we want to have about a 3-inch drop between the impervious surface and the pervious surface so that we can allow for some growth of vegetation without impeding the inflows onto the buffer. Of course, healthy topsoil is a precursor for healthy vegetation. MHFD's topsoil management guidance goes hand in hand with many of the SCMs in Chapter 4. Without healthy topsoil, it's unlikely that an RPA will achieve the density of vegetation needed for effective treatment. We also include expanded guidance on level spreaders in the front section and guidance on protecting RPAs from compaction during construction. The fact sheet includes general guidance on RPAs as well as specific design procedures and criteria for buffers and swales. We tried to be somewhat less prescriptive with the criteria, for example, with the minimum buffer widths, to encourage more widespread implementation of these practices. In many places in the urban environment, pervious areas can be strategically placed to serve a water quality function. A really good exercise during site plan development is to carefully evaluate all of your pervious areas to avoid missed opportunities where separate pervious areas that do not receive runoff from impervious areas can instead be lowered and turned into receiving pervious areas. The green roof fact sheet, now named the Rooftop Systems Fact Sheet, has been updated to incorporate lessons learned both nationally and locally, including research by Dr. Jennifer Busolo from Colorado State University. The fact sheet includes both extensive and intensive green roofs, although the shallower extensive green roof systems, which typically have about 6 inches of substrate, are the primary focus of the fact sheet. Additionally, blue roofs are included in the fact sheet as an option for rooftop detention of the WQCV without inclusion of vegetation. In a lot of cases for blue roofs, you'll need to provide an orifice to slowly release the detained water. Green roofs are recognized as volume-based SCMs that control the WQCV primarily through evapotranspiration. In most cases, an orifice control is not going to be needed for a green roof. Community values of green roofs are recognized as gardens in the sky, as well as providing an option for water quality in ultra-urban areas where space constraints are present. The design procedure in the fact sheet was reviewed and updated with significant input from Dr. Busolo. This includes additional guidance on the substrate or growing media, irrigation requirements, and a suggested plant list as examples. Recent research by Dr. Busolo at CSU has been integrated into the updated fact sheet, including a suggested planting list along with general guidance on characteristics of plants that are good candidates for green roofs. Other considerations for plantings given green roof microclimates, wind, sloped roof applications, and other factors are also provided in the fact sheet. Irrigation is necessary for the success of green roofs, but CSU's research shows that green roofs can survive on a minimum of about 5 inches of irrigation over the growing season, which is significantly less irrigation than would be required for most types of turf. The bioretention fact sheet was an area of significant updates. Bioretention is an SCM that we want to strongly encourage due to the runoff reduction benefits, the effectiveness of treating runoff, and the potential to provide stormwater facilities that are attractive rain gardens to the surrounding communities. One of the struggles with bioretention in a semi-arid environment is how to support vegetation. Appropriate media is important, and we made some updates to the media mix to retain somewhat more moisture to better support vegetation. Irrigation is also really important, and this will typically be required during establishment and may be required over the long term, depending on the types of vegetation and the severity of future droughts. The fundamental approach to sizing of drain times has not changed. Components of bioretention are similar to other storage-based SCMs with inflows, outflows, and a storage volume. What makes bioretention unique is the media, which serves multiple functions, including supporting the growth of vegetation, providing filtration of runoff, and providing opportunities for adsorption or absorption of pollutants as they filter through the media. Stream has created new renderings that are included that show how the various components fit together and illustrate outlet concepts for WQCV only and bioretention facilities that integrate full spectrum detention. One of the most significant changes to the bioretention criteria are updated criteria for media. Dr. Scott Struck, formerly of Geosyntec and now with NREL, conducted an extensive literature review and study of this topic to develop new recommendations. Previously, we recommended 80 to 90% sand, which provided really good rapid drainage, but didn't provide enough organic matter or nutrients for healthy plants. We have reduced the recommendation for sand content to 70 to 80% in this fact sheet, and we expect this will still provide effective drainage to meet the 12-hour drain time, but the additional silt and clay content will help to provide nutrients to the plants and also hold more moisture that can be used by the plants. An important thing to understand with bioretention media is that we have a different approach than many other regions in the U.S. For use within MHFD, media is typically created from a living natural topsoil by blending the soil with sand until you achieve the desired media proportions. As a result, the supply of media is contingent on the supply of suitable topsoil. As a part of this fact sheet, Mile High Flood District conducted a survey of media suppliers across the Front Range and found that the large majority of media suppliers would be able to meet the specification that we now have in this fact sheet for bioretention media. So it should not be hard to obtain this material. We also updated the plant palette and expanded it as a part of the update to the fact sheet. The native seed mix hasn't changed a whole lot, but we added a table for container-grown plants and plugs. These can be extremely helpful, especially if you need to have rapid soil or media stabilization, as opposed for waiting for seed to germinate and grow. One final update to mention relative to bioretention is the concept of an internal water storage zone, or IWSZ. This detail shows how an IWSZ can be created with an upturned elbow. The IWSZ is suitable for partial infiltration sections, and runoff is held below the invert of the upturned elbow and can slowly infiltrate into the subgrade between events. Some research has shown that IWSZs can create anoxic zones at the bottom of the SCM, and that this can be beneficial for denitrification. This practice has been used elsewhere for some time on the East Coast and the Pacific Northwest, and it's a good approach to use in Colorado, where your soils are suitable to allow for slow infiltration of the stored water over the time between runoff events. Sand filters are very effective SCMs for water quality treatment, but are not used widely as bioretention, largely due to aesthetics. As a part of the update to Chapter 4 of Volume 3, we did not change a lot relative to the sizing or material used for sand filters, but we tried to provide some more examples of where these can fit in an urban landscape. One of my favorite applications for sand filters is for electrical substations, like the photo on this slide shows. Substations are typically kept free of vegetation, and they do this by applying a lot of herbicides. As a result, vegetative SCMs that receive runoff from substations usually don't do too well. Sand filters are a really good fit because they're low maintenance compared to vegetative SCMs, and they can fit with the industrial aesthetic of a substation parcel or other type of industrial site. As with other SCMs, we define sand filters by the components that comprise the SCM. Design of many aspects of the sand filter, the inlet, the outlet, the underdrain, and so on, are addressed in the front section of Chapter 4. The examples to the right in this photo include a couple of sand filters. One is an underground sand filter from the Denver Botanic Gardens, that's the top photo, and the one on the bottom is a linear sand filter beside a parking garage. Sand filters are stormwater control measures that can easily be adapted to work underground, and this opens up the opportunities to use this SCM for treatment of runoff from streets and highways. When considering a sand filter, or any SCM for that matter, near a building, you need to be sure to analyze and mitigate the risks of infiltrating water. Table 4-3 in the front section of Chapter 4 provides a framework for assessing risks related to infiltration-based SCMs. The next fact sheet I'm going to discuss is related to permeable pavement systems. The same basic types of permeable pavements are still recommended: permeable interlocking concrete pavers, concrete grid pavement, porous grass pavement, or reinforced grass pavement, depending on your specific application. Monolithic permeable asphalt and permeable concrete are still not recommended due to poor experiences with durability in our climate. We have updated criteria to better follow guidance from the International Concrete Pavement Institute, ICPI, and we expect that this will help to resolve some issues between the criteria in previous versions of the MHFD fact sheet versus criteria that are recommended by manufacturers, which tend to follow ICPI. We had a lot of great input from Curtis Kostecki of Creative Civil, who has designed and overseen installation of more permeable pavement systems than anyone else I know in Colorado. Curtis provided a lot of new photos and details from his projects that we adapted to update this fact sheet, including tree well details, new outlet details, and new perimeter barrier details. The basic aspects and components of permeable pavements haven't changed, but we have added some additional discussion on some aspects, including community values. Permeable pavement systems have the potential to add a lot to a community, perhaps more so than any of the other types of SCMs, due to the fact that they create a multi-use surface. As the photo in this slide shows, pavers can create a really attractive surface in an alley or other traditionally impervious location, allowing for infiltration and providing stormwater treatment beneath the ground. We've also provided additional emphasis on the importance of providing an overflow path, Even when you have underground SCMs, it's critical to define an emergency overflow path on the surface in case the outlet of the permeable pavement system becomes clogged. These are a couple of examples of new outlet details. The one on the left is for a permeable pavement system that provides only the water quality capture volume. And in this detail, you can see that we have a restrictor plate on the underdrain coming out of the media into the outlet structure. That is what regulates the drain time. If you get larger flows, they can spill over into the maintenance holes and then go through the outlet on the right-hand side of that detail to the storm drain. The detail on the right-hand side is for a full spectrum detention system outlet, and in that case we don't put a restriction on the underdrain, but instead we construct an outlet structure that has multiple stages within the outlet structure box. This has controls for the WQCV, the EURV, and the 100-year, and the top of the riser can be left open for overflows for even bigger events. Of course, if you get a really big event, you could still have water flow over through the maintenance holes, or this could be the case if you have a really large event where your surface emergency overflow path is activated. Jim Williman and Tracy Bolger of Muller Engineering led the update to the EDB fact sheet, which provides guidance and criteria on one of the most widely used SCMs in our region. Major updates included addressing issues with clogging of well screen and small orifices. We added guidance on designing for base flow conditions, which may change over time as a watershed develops. We've provided updated outlet details. Generally, we're trying to use fewer larger orifices while still having redundancy. We also like to use bar grading versus well screen when we're able to, and the new details provide a variety of configurations. We provide some new guidance on alternative to micropools, and finally there are new criteria related to vegetated low flow channels, which provide benefits for water quality and community values. In my opinion, the table shown on this slide is one of the most important updates in this EDB fact sheet. I expect that we've all experienced issues with small orifices or well screens that clog. This creates a lot of maintenance headaches and it diminishes the effectiveness of the SCM. EDBs should not be used for small sites that have less than 2 acres of impervious area, and they should be used for caution for sites that have between 2 and 20 acres of impervious area. When you're in that 2 to 20 acre range, one thing you can consider is using these V-shaped debris deflectors that are shown in the photo on the bottom. That is an approach that Muller Engineering has been using with some effectiveness to keep debris from clogging the orifices. Sites that, when you size sites that result in very small orifices that have to be protected with well screen, that can notoriously clog with debris even when you properly size the well screen. So when you get down to the area where you have orifices that are so small that you have to protect them with well screen, in general, we would recommend that you consider an infiltration or filtration-based SCM, like a sand filter or a bioretention, which is a much better choice than an EDB for smaller sites. We're also now recommending fewer orifices than in the past version of the fact sheet. We recommend 2 orifices for the WQCV, which provides some redundancy, and then there is a 3rd orifice for the EURV when you're designing for full spectrum detention. Also, you have to be cognizant of large watersheds due to base flow, and you have to provide the WQC for the entire upgradient watershed. And for these reasons, you might consider using multiple sub-regional EDBs instead of a single large on-channel EDB, and that may be a better approach for larger watersheds. We've also added new outlet structure details for configurations of the WQCV treatment and full spectrum detention with different combinations of micropool and trash racks. This detail shows an option for a sand filter micropool alternative, which is a new option in Chapter 4. Muller also expanded guidance on trash racks, including well screen and bar grading. Typically, at a size of 20 acres of impervious acre or larger, you can use bar grading instead of well screen, and this has huge benefits in terms of minimizing clogging and maintenance. Orifices that are smaller than 1.25 inches in diameter, or their minimum opening dimension, will require well screen. And again, when orifices are this small, it's much better to consider using bioretention or sand filter instead of an EDB. Another significant update is the addition of vegetated low flow channels. Concrete low-flow channels have benefits in terms of ease of maintenance, but they don't provide a lot of environmental or community benefits compared to vegetated low-flow channels. Vegetated low-flow channels allow for infiltration of a portion of base flows, and they provide enhanced treatment relative to concrete low-flow channels. They also maintain green space across the bottom of the EDB that provides habitat and community value benefits. Retention ponds and constructed wetland ponds have combined into a single fact sheet given the similarities in design. There have not been major changes in the design criteria for these SCMs, but the updated fact sheet provides new graphics and expanded guidance on integration with the surrounding site and community values. These SCMs come at a higher cost than some others due to the need for water rights. So to justify this additional expense and administrative burden, these facilities really need to provide significant community values. Of course, safety must always be a consideration when designing a facility that will have ponded water, and the fact sheet provides guidance on safety measures, including edge treatments to discourage access and safety benches in areas where there will be public access. We also included new photos of retention ponds and constructed wetland ponds that are well integrated with surroundings as examples. The photo on the left is a large retention pond at a development in Westminster. This pond is really a centerpiece of the development, and it's a really active area for recreation. The photo on the upper right illustrates a constructed wetland pond, which is an SCM that provides a high level of water quality treatment and can also enhance aesthetics, habitat, and provide community values by creating SCMs that have a natural appearance. The manufactured treatment device, or MTD fact sheet, has been significantly revised. Key changes include the following. The fact sheet focuses now on two primary categories of MTDs: sedimentation-based hydrodynamic separators, also referred to as HDSs, and filtration-based MTDs, including high-rate media filters and high-rate biofiltration. Hydrodynamic separators are identified as suitable only for pretreatment. These may be suitable in lieu of a forebay in a space-constrained area, or potentially as on-site treatment when there's a down-gradient regional facility. High-rate media filtration and high-rate biofiltration are suitable as standalone treatment for water quality objectives because they rely on more rigorous treatment through filtration. Local jurisdictions will determine what types of MTDs are allowed within their boundaries. The fact sheet provides information on maintenance considerations and also general steps included in design, while recognizing that the design process may vary depending on the manufacturer. A major change to MTD design is that the new fact sheet provides for water quality peak flow rate as the basis of sizing, which is different from the previous fact sheet, which was typically based on a 2-year event. The water quality peak flow rate, or the WQPF, is the peak flow that's based on the 2-year CUHP rainfall distribution with a design storm depth equal to 0.6 inches, in other words, the water quality event. The WQPF can also be calculated using the rational method to give you only a peak flow. The supporting analysis for the WQPF is provided in the Mile High Flood District Memorandum that I'm showing you here that's available on Mile High's website. It's also now included in the runoff chapter of the MHFD manual, which is Chapter 6 of Volume 1. MHFD recommends third-party verification of performance expectations and identifies several programs for this purpose. At the time that this MTD fact sheet was prepared, MTD certification protocols are still evolving. The recognized protocols at this time include the Washington State Department of Ecology TAPE program, particularly for filtration-based practices, and the New Jersey Department of Environmental Protection HDS protocol for HDSs. Future programs recognized in the fact sheet that are expected to be relevant to MTD certification within the next few years include the STEP program, that's STEPP, which is managed by the National Municipal Stormwater Alliance, and ASTM E64, which is going to be a new standard coming out soon. That brings us to the end of this webinar. You can access Chapter 4 of Volume 3 at the link provided on this slide. If you have any questions, keep in mind that we're going to be holding office hours in the near future, so please monitor the MHFD website for this and other upcoming training opportunities. Thank you for attending this webinar.